Okay, so yeah. We're going to start with this question 1 here, and it's about vectors, I believe. As I draw and label a vector diagram to show his total journey, then calculate his resultant displacement. Okay. Easy enough, I hope. Okay, please tell me my connection's good. Okay, so let's start with what we got here. He says he walked 747 meters west to repair a gate. So we'll just draw that one first. There it is, and that represents this much. And I'll just write that. When he was finished, he turned around and walked, oh, it does say west, doesn't it? Let's do it proper then. West. Okay, and then he walked 984 east to repair another part. Draw and label a vector diagram. Okay, so we could put it right over top, but for the sake of clarity, so you can see, you know, the vectors more clearly, don't draw exactly on top, just move it down a little bit and then draw the second vector. Now you might get confused, which one did you draw first? Well, I like to just, you know, draw the first one on top and then the next one just below it, so I know which one is actually the first one. So there's the start, goes here, he's at the west fence, then he starts to walk back east on the same path, okay, so this is just the same as just here. He walks east to repair that part of the fence, so now he's there. So our resultant is really from, here's the end now, there's the beginning, there's the end, so we draw our resultant from the beginning to the end, and that is the resultant one, okay? I should label this one too, just so I remember which one it is. Yeah, everybody good with this so far? Vector diagram represented by arrows, guys. Should be able to do this one pretty quickly. You know, this is 4 marks, yes, but you should be able to do this fairly quick and find the resultant. So that is basically taking 700 something. I don't know, which depends which one you label as positive or negative. So let's say east is positive. So basically what I'm doing is R equals, this is the positive value because it's going east, 984 minus, or we just say plus the negative, really, okay, the west, which is the opposite direction. And so when you take this and you minus this part, you're left with the resultant, which is yeah, that one, 239 meters. And put the direction, so east. Okay. Let me just move this here. Okay, so we'll just keep going here. Hopefully you got that. If you need me to slow down, just let me know. And yes, I will slow down. Okay, we're looking at question 8 here. And it's just saying that there's a runway, and the runway is this long, so that's the length, a distance, whatever, so it's going to be our S, our displacement. It says the aircraft accelerates that much, so there's our A, acceleration. starting at along this runway, starting at one end and taking off 200 meters before reaching the end. Okay, so this is not quite the S then, really, okay? So we need to take off 200 before the end of the runway, which is this long. So we're just going to subtract 200 from that, okay? If the aircraft was initially stationary, okay, good, that's U. Calculated speed when it takes off, all right, that's V. Great. Show all working in it. So now we have our 1, 2, 3, 4 variables, and from that we're going to look at our formula data sheet and choose the correct motion equation. And the correct one for this situation, based on those variables, is v squared equals u squared plus 2as. Okay, so what is our final velocity? Well, this is squared, so we're going to have to take the square root of the whole other side. That's 0 because it started from rest, plus 2 times our acceleration here. And then our displacement is really going to be that much, which is only 1020 meters. Okay. Yeah, from that we should be able to give our answer. Okay. So you should plug that into your calculator. And if you get it right, you should get this answer here. Where's my calculator? Just do this. So the square root of 2 times 0.785 times 1020. Oh, I guess I don't need that. It's all underneath already. Should be 40.0 meters per second. Okay. So that was question number 8. It says give the appropriate unit, so I guess you get a mark for that, that one, that, and that. Or at least for this part here, understanding that the distance is minus that 200. Okay, please be careful when you read the questions to understand things like that. Okay, that can easily be overlooked, and you plug in this number here. All right, moving on to question. What question is this? Hold on, I got my list here. Should have been question 12. And instead, I got page 12. Okay, it's all right. I got it here somewhere. Where is it exactly? There it is. Okay. Should have been question 12. Page should have been question 13. Yes, I'm sorry. Question 13. Correct. Whew, I just got confused there when I said on a hot day. What do we need temperature? Anyway, Sam stepped off a bridge into the water below. All right. He's just, I think he's going swimming. He's not jumping off a bridge. Using the idea of conservation of energy. All right. Calculate Sam's speed in meters per second when he reached the water 350 meters below. Show all working. Okay. So when he jumped off the bridge, obviously his velocity was 0. We want to use the conservation of energy to calculate Sam's speed, not kinematic equations, okay? We could do that, because we know the distance, we know gravity's acceleration, and we know the starting velocity. So we could do that, but that's not how you're going to get the mark. The mark is to use conservation of energy, and that is when Sam's at the top of the bridge and he falls down to the water. That's 3.4 meters. Now that is the height. And what happens is, as his height reduces, as height goes down, what happens is his velocity will go up because he's losing potential energy. So he's losing EP and he's gaining kinetic energy. So there's the two types of energy, okay? Now that conservation of energy means that as potential energy reduces because his height reduces, his kinetic energy increases because the potential energy is changing to kinetic energy. He's going faster, so he's going to have more energy because of that. So the equation for EP is mass times gravity times the height. So your weight force and then the height that you're from where you're going to land, okay? And then the kinetic energy part is, well, it's going to be 1/2 of mass, velocity, and squared, okay? So there it is. It's changing from this to this. So it's saying at the bottom, he's going to be exactly 0 height. So there's no more potential energy, and all of it is kinetic energy. Okay. So very easy for us to do. The potential energy at the top is equal to the kinetic energy at the bottom. Because up here, he has 0 kinetic energy, remember? His starting velocity is 0. But as he transitions downwards, down here, he has all kinetic energy and no potential energy. So at any moment, we have both of these energies, depending on if we're a height from a surface we're going to go down to, or if we're moving yet, or how fast we're moving, okay? So for us, this is going to be easy for us to do. mgh, 1/2 mass velocity squared. You notice that in these equations, this mass is part of the equation. However, the question doesn't tell us about Sam's mass at all. Well, according to algebra and math, when you have the same two things on either side of an equal sign, what happens is they just cancel out, and we don't even have to, do anything about it. We don't need the mass because both the masses are both equations, and it doesn't really change the other numbers. Okay, if we can cancel them out, then we cancel them out. Now we want to find the velocity at the bottom where there's all kinetic. So now you can see we only have the half v squared g and h. I'm just going to rearrange this formula so it's only v. So this, instead of multiplying by half on this side, it would divide by half on this side. But divide by half is just 2 times these two. So g and h. I'm putting it on this side. And then all I have left is the v squared. And we know that for v, I need the square root of those two. And that's the whole equation. The velocity at the bottom equals the square root of 2 times the gravitational acceleration and times the height that he jumped from. Okay? So that's it. 2 times 9.8 times 3.4 meters. Okay? And I don't know, the final answer would be about 8.16 meters per second. Okay? And that's it. Understanding how the height difference and how the total energy, okay? So at the top, total energy is only EP because it's not moving. And then as he drops down, the total energy is the combination of the remaining height that he still needs to fall, plus the kinetic energy he gained as he fell. All right? So right at the bottom, when he no longer has any height, it's all kinetic energy now. And so if we understand that, then we know that all the EP at the top is going to be equal all the EK at the bottom. And at the bottom, there's no more EP. And because we weren't moving at the top, there was no EK at the top. Okay? Potential energy, kinetic energy. EP, EK. All right. And then when we equate the two, because it didn't tell us mass, we don't even have to worry about mass. They're common factors, so we can take them out and not use them in the calculations. And then we just rearrange to solve for V. Okay. Okay, let's just double check my checklist here. Question 15, I believe, is the next one. No, 17. Keep reading it wrong. Oh, there it is. Okay, so this one's about Newton's laws of physics. And we should know all three, yeah? In this game of cricket, this is the batsman. All right, so this game, you know, these guys, I don't know if you've ever seen cricket, but they wear these big things on their legs, and it looks like that. It's to protect their legs from the ball because the ball is really hard. And so this is the front. This is where the ball comes from if they get hit by the ball. And then their legs, you know, back here. Like that. So we got the padding. We have the plastic inside. Okay, let's see what this question says. So batsman wears pads on his legs to protect him from injury by a fast-moving ball. Each pad has 3 centimeters of padding between it and the batsman's leg. And each pad has a rigid plastic slats built inside. Okay. Using your understanding of one of Newton's laws, how the padding reduces injury to the batsman's leg if it is hit by a cricket ball. Wow. Okay. Well, I think if you go back to your notes and if you look at your student book, one of the things that they mention, this is about momentum. Okay, it means that the mass and the velocity of the ball hitting him, hitting this, is spread out over a longer time because that's what the padding does. It compresses, it gets smaller, and it takes time for it to do that. So the force of the ball hitting this will increase the time. So this is actually Newton's second law. Okay? Can I type in here? Where's my type? So that's what we say. Whatever law we say it is, we say like that. So according, oh man, what is the pause button? Give me a second here. I just check to see what is the D. Okay, so I no more typing. Oops. Sorry. I'll just say that again quickly. According to the second law, Newton's second law, that impulse is force times time, and it equals to the change in momentum. So, and because the velocity of the ball is fixed and the mass of the ball is fixed, then that's constant. And if we can reduce the time, we can increase the time that the ball changes its momentum, then the amount of force acting on us at any single point in that time is going to be less. Okay, the force is decreased. Okay, anyways, sorry guys, I can't type anymore. Okay, so that's why I don't type. A toy rocket has a mass, good. It's fired straight up. Okay, something like this, fires straight up. We know acceleration is going to be downwards. So I'm just going to write that right away so I don't forget. The chemical energy provides this amount of force. So we have applied force, right? That's the engine doing that for a certain amount of time. Negligible mass, we don't have to worry about mass. Yes, we already know the time. Okay. So it has mass. There's an applied force. It's a rocket going straight up. It says, draw label vector diagrams from X on the rocket to show all the forces acting on the rocket in the first 1.8 seconds of flight. Include any frictional force. Okay. Wow. So the lengths of each arrow should represent the approximate magnitude of the force acting on it. Okay. So that means that the more force something is, we should have a longer arrow, right? All right. So we should have. It is on it's on Earth, so there's always gravity. Yeah. And this applied force is the thrust force, really. So that should be upwards and a little bit longer. Otherwise, we would not be accelerating upwards. So we have to, you could say FA, you can say F thrust. Whoops, what am I doing that one? Up to you. And then there should be one more. It doesn't have a lot right at the start, but after a few seconds, it should have a little bit, and it should have a little bit of air resistance. Okay, so from that, you should have three forces: thrust or applied force up, down for weight force, Fg, the friction, air friction, so that was downward because the motion is upwards. Okay, that's it. So this remember this one should be longest because that's the direction that this accelerating upwards. So the net force should be upwards. Okay, so I'll give you guys a few minutes to look at this one and try to figure it out. And I'm going to ask you guys to help me along to do this one. So the net acceleration of the rocket is affected by the thrust of the engine and the force of gravity. Calculate the acceleration of the rocket just before its engine stops working. Ignore any other forces acting on the rocket. Okay, so in this situation, that means there's no more air resistance, so we don't have to worry about that. It's just thrust and gravity. So we want to find the net acceleration. Okay? Give you a little hint. There's two ways we can find net acceleration. We could find the net force. And then from that, you can find the net acceleration. So you would have to know, in this case, I think we do know, there's the net force of the rocket engine, and then you know weight force. You can calculate weight force. That's one way to do it. So I'll show you the first is find the net force first, okay? And then find the acceleration. The second way is just to find the different acceleration. So the acceleration due to the thrust, and then you know the acceleration due to gravity, because that's always the same. So the net acceleration would then be those two. The acceleration thrust due to the thrust minus the acceleration due to gravity, right? Okay. All right, so has anybody given me a thought on how we might do it the first way? Okay, so you think that for this, you just want to find, you mean you, okay. So she did this. F net is going to be the thrust, right? The applied force minus the wave force, right? That's what she has here for the negative. So, okay, so we got 8.5 minus, it's in here. Why it's minus? Because the thrust is up and gravity wave force is down. So 0.65 times 9.8. You could make this negative. Yes, you could add those two together, but this would be negative. Anyways, yeah, you can get that net force of I don't know, what would that be? What would that be? I have my calculator out already. So 8.5 minus okay. So there's the net force. And if you want to find, now that we have the net force, then that is going to give us the net acceleration. And the acceleration would be net force divided by mass, which is 0.65. Okay. So that 213 divided by 0.65. And what we end up with is this number 3.28. Okay. So 3.28 meters per second squared. And now if we do it the other way, let's find the net acceleration. So if we take our acceleration of the thrust, it should equal to the thrust force. I don't want to spell thrust again. I'm going to use FA time divided by the mass. So we got 8.5 divided by the 0.65 of the rocket, and what you get is so 13.1. Okay, so that's the thrust. But now, of course, gravity is also pulling down on it. So the net acceleration, as over here, is going to be this 13.1 minus gravity. And that, fortunately, we already know. We don't have to calculate anything. It's 9.8. And you see it comes out to exactly the same value, 3.28. Okay, so there's two methods to doing this. You can do it the old-fashioned way, which we know net force, or we can find the acceleration that the amount of thrust would create, and then subtract the gravity's acceleration, which is the opposite direction of that, and it comes out to the same exact answer for the net acceleration. Okay. So that's just two methods of doing that. Okay, any questions? Should I just leave this here for a second? We'll take a little break after this one question. This question is part C, D, and E. Okay. Okay, so it says calculate the height in meters reached by the rocket the moment when the engine stops working. If you're unable to calculate it, okay, so we know acceleration. We know the net acceleration, okay, is that. So we don't have to worry about gravity now. It's 3.28 meters per second up. We know from the question that the engine works for 1.8 seconds. Good. And we know that it's at rest, right? So we know that U is 0 because it starts from the ground. Okay? So U equals 0, time equals 1.8. Okay, now knowing that, I'm choosing my equation, and the formula data sheet tells me that this is the most appropriate equation for the situation. Now, because everything is upwards, and we don't have to worry about gravity because we already figured out the net acceleration, then nothing has to be negative. So this is 0, and it's all just acceleration, and that is 3.28. And the time is 1.8 squared. Don't forget that square. It's so easy to miss it. Just look and double check that you have that, okay? That's why I like to put my numbers with the brackets so I know exactly what I'm substituting, and anything I substitute, it still has any indices affecting it. Okay, so using that equation with those variables in there, I should come up with some 5.31 meters. Yeah, that's it. I mean, it wasn't a very long burn there. Okay, so that's part C, 2 marks for that. Calculate the velocity, okay, in meters per second of the rocket after 1.8. Okay, so we want V, really, okay? If you cannot calculate for part B using acceleration, okay, we're still going to use our original one. So we want to know that. Now we have time. We still have time. Time's still the same. U is still the same. I don't want to write it again. A is still the same. So those are the variables we have now, and I'm looking at my formula sheet, and again, it tells me which formula has those variables. And it's those ones. And because I started with 0, basically it's just acceleration, which was 3.28 times the time. And this time just double check up here, no indices. And so again, kind of an easy one for us to do, I think. Acceleration up, time. Calculate 180 meters after the velocity stops. Yeah, that's it. Okay. Let's double check our answers. There's got to be more than one way to do this, because maybe you decided to use the distance. Okay. If you did that, then we wouldn't need time. But I mean, we're given time here. Why not use it? Okay. So there's other ways to do it. If you decided to use S instead of T, well, then it would just be this way. And honestly, it's not going to be that much different. and S is going to be 5.31 times 5.31 as well. Okay. If I put that in my calculator, I think I'm going to come up with the same answer, right? Because you got to take the square root of this too, right? So V is going to be equal to the square root of all that. 2 times 3.38 times 5.31. Okay, so square root of all that. Don't forget the square root, guys, to do that. So 2 times 3.28 times 5.31. And you can see it actually comes out to the same exact answer. Okay, it says in meters per second, so I guess we don't have to write this unit. So always more than the nice thing about the kinematic equations in motion is that there's more than one way to do it. Let me just double check my thing here. Okay, I did get something. Okay, last one before we take a little break here. Calculate the maximum height in meters reached by the rocket. Show all workings. Okay. Okay, calculate the maximum meters reached by the rocket. Okay. Hint, when the calculating displacement after the rocket stops working, use the velocity calculated in part D as above as the initial velocity. Okay. So for us, when there was the engine working with the acceleration of the net acceleration, we already had S equals, right? Calculate the height meters reached by the rocket the moment the engine stops working. Okay, so it's moving upwards at that acceleration for that long, and you get that height. Okay, and it says now we want to know what is the distance when U is this value now. Okay, so now we're looking at two parts. Okay, so if for you, you can do two parts to this. There is from U equals 0 to up here to U equals 5.9. Okay, and then at that point, the rocket and the acceleration is 3.28. And at this point, what happens is there's no more engine. There is the beginning of our new second part. We will actually want to find, this is S1, this is S2. Now we want to find S2 to find that total height. Okay, we know that at max height, V will equal 0. And we know that in this situation, there's no more net force of 8.2 feet. What happens is gravity takes over now for acceleration because there's no more engine, and it's a negative value because it's opposite now. Okay, so this was up before, now it's down because of gravity. And essentially, we are calculating this. So this second part, real easy for us. Okay, from those variables that we don't know the time, so it's just this. Again, we're going to use this equation, but this time everything's a little different. We'll rearrange for S minus U squared, all divided by 2A. Okay, and luckily for us, V0, we're going to have a negative value up here for our U. U is 5.9. Okay. 5.9. I'm just going to disregard the 0 for simplicity. And our acceleration is going to be displacement. Yeah. Okay. what is it, 2 negative 9.8. You see, it all works out. There's going to be a negative from the acceleration, and this square is going to be still negative. I don't know what that is. It should work out to about 1.78 meters. Okay? And once you get that, that's not what it asks us though. It says calculate the maximum height reached by the rocket. So there's our maximum height is S1 when there was the engine working, and then S2 as the engine's off and the gravity starts to slow it, the rocket's ascent, slows down the rocket from going up, and then it stops at this maximum height, and then that means these two we add together. There's S2. We're going to add that to the original height that it started at, which is 5.31. Is that right? 5.31. Yep. And then there is our total, and then there's the max height. You will write this a little neater. You can write a final answer so that you get something much better than what I got. 9, 10. Did I write down the right answers? Yeah. Okay. Yeah, that's what I got. Okay. 2, 2, 2, 9, 10, 6, 6, 7, 7, 7. I'm going to add the 1. There's 7. All right, so we're just going to take a little break now. We'll come back and we're going to start. We'll do a little graph, so you can grab yourself a little graph paper from one of your notebooks, I guess, because we'll make a graph. Okay, you should practice making a graph. It's almost always a graph, and we're going to do this number 24. Okay, so why don't we come back at about 2:05 or 2:10? Which one would you guys prefer, 2:10 or 2:05? The 10, please. So 2:10. Only one person has an opinion. When someone asks you your opinion, just say, "No need to be shy." They know they're not gonna say their opinion. Okay, 2:10. We'll come back. Okay, see you guys in a minute. I mean 10 minutes. Since I plotted this, according to the scale up here, I wish I had pressed recording. Oh well, you guys didn't make it. The recording's a little spotty. Okay, so now that we have this line of best fit that goes through the data points that we plotted from our table above. We're going to find the 2 points here that meet at intersections. Very good one. So this one here and one there. And then so our gradient is going to be, y2 minus y1, the change in y divided by the change in x, so x2 minus x1. Okay, so y2, this is 2, so there's 22 here, minus y1, which is down here, is 11, divided by x2, which is 9, minus 0.5. There we go. Okay, so we got 11 over 0.5. I know 85. And you should get a value for that. Let's calculate that out. It is 11 divided by 8.5. So yeah, about 1.29. Yeah. But it also says include the correct units. Well, what are we doing here? the top, the y represents meters per second, and the bottom represents unit of time, s. So it's going to be meters per second squared because we're dividing by seconds again, okay? So really, anytime you have a VT graph, you guys know it represents a slope. The slope represents acceleration. That's why the unit's like that. Okay, so the gradient is acceleration. Okay, I think, any questions? Now, something like this is a bit of a, it's an estimate because that line of best fit's an estimate. And if you read the beginning of your paper, am I showing you guys the whole screen? Yeah. Okay. Then you know that actually you only round to two significant figures for estimates. Okay, so if you wrote 1.3 here, that's totally fine too. Okay, any questions? Everybody's good? All right, let me set this back up. Proper thing that we were doing. Oh, oh. Okay. Okay, I think that was the last of that question. I did want to do a couple more momentum ones, and as Nee said, something about force. So, I did have something here. Oops. Somehow I lost the connection to that one. No problem. I think I saw something here. Yeah, that's it. Just let me open it here, and then we'll get onto it. Yeah. Okay. So I want you to take a minute and read this question and tell me what you feel is the best way. What part of motion are we talking about here? Okay, so what topic of motion are they trying to get you to understand and use those concepts to solve this question? Think about the information they're giving you. Okay. That was my finger. Ouch. 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 So what do you guys think? What is the topic this is looking at? Well, what information does it give us? it gives us a mass of the bolt. It gives us the velocity of the bolt, its direction. And then this is a target. Yeah. Target's mass and the velocity of the target. It asks us to calculate the velocity of the target and the bolt after collision. So another thing with collision, like hit, okay? Anytime you talk about collision and you talk about mass moving, it is momentum, correct? Okay? So momentum, we gotta know, we gotta understand something about momentum. Okay, so momentum is P and is the motion of mass. So that's it. It's just that. But there's something called conservation of momentum, meaning that the momentum, the total momentum of everything that's involved, in this case the bolt and the target, together their momentum will be the same before the collision and after the collision. So the before momentum, that's what conservation means. There's no loss in momentum. Okay? So we gotta consider one-way positive because that has directions here that affects how things work. So we'll just say this way is positive, that's east. And let's take a look at the momentum of the individual ones before and after. So the total momentum is P before equals to the momentum after the collision. Okay? And it's the total momentum. It's the momentum of this and the momentum of this. Alright, so let me just erase some of this and move this up a bit. I forgot. I used to be able to move all this, but now I cannot. Yeah, for some reason it can't now. I'll just erase it. Okay, so P before equals P after. So how would you do this? What is the momentum of the bolt? Well, again, it's mass of the bolt. We'll say it's 1, and we'll say the target's 2, times the velocity, starting velocity of it, plus the momentum of the target, which is the second one, and its initial velocity. See? We're adding them together. That's their total momentum. And it's going to equal the same momentum afterwards. So their momentum afterwards means their mass is the same, but their velocity should change. See? V over here and U before. And then the target, its mass is the same, but its velocity should change. Okay? If we read this carefully, though, we notice that for this side, calculate the velocity of the target and the embedded bolt. That means they become one. They become a single mass and they move at the same velocity. Okay, so we'll just rearrange this side a little differently. It's the same velocity, but the masses add together. Okay, so mass 1 plus mass 2. And because they're a common factor, the velocity is the same, we just move it to the outside. See? This is still multiplying these two. But we add these masses together before we multiply it, okay? And then that side stays the same. Okay, so now if I make, you know, I substitute the numbers. So this, remember everything has to be in the base unit. So the mass of this one is in kilograms, so 0.15 kilograms. And this one is 5 kilograms. For us, we don't care about decimal places and stuff in our calculations. So 0.15 plus 5 equals V. And on this side, we got 0.15 and 24 meters per second plus the mass of that, which is 5 times 1.4 meters per second west, okay? We can put all that in. So just give me a second. So I'm going to put in the negative here for the velocity of the target. Remember, because we said this way is positive value direction. So we're going to put that negative in there. It's going to be helpful for us because we don't know if the bolt makes the whole thing move to the right, or because the momentum of the target moves everything to the left. Okay, so we do need to put the negative in there to indicate direction, because the final answer, if it's positive or negative, is going to help us determine what the final direction is as well. Okay, so why don't we do this part? I'm just going to do step by step so that we don't lose anything here. So 0.15 times 24, we get that number. We have 3.6 positive plus, this side's going to be negative, 5 times 1.4. Okay, so that's 7 minus 7. Okay, this is actually going to be negative. And then this one's 5.15 V. So now we can get V. V equals this. Okay, so 7. Negative 7. Oh, negative 7. I'm just going to do this way so you can see it more easily. It's going to give us negative 3.4. Okay, so negative 3.4 divided by this value of mass for the whole thing now. So the answer divided by that. And there we have it. The new velocity is negative 0.660 meters per second, or we can say 0.660 meters per second west. Okay, remember, negative just means the direction is opposite the positive direction. So the whole thing actually is going to move this way to the west at that new lower velocity, because the mass of the target was so big that it caused that. Okay? So it's okay to leave your answer like this, negative, that's fine, or you can just realize it and say oh, positive value, but say the direction's west. I'm just going to zoom out a little bit so you can see the whole thing. Again, constant of momentum, meaning that the momentum of both objects is going to equal the momentum afterwards. And if we allow that, what happens is when they collide and then they stick together, we consider their mass as 1, and that means their velocity will be exactly the same. And if that's true, then we can just take out the velocity, which is multiplied to both the masses, but then added together. So it's just like factoring out the V, so we can solve for V. Okay? So together they move 0.66 meters per second west. Momentum. Okay. This question is about understanding Newton's laws of motion and forces and whatnot. Okay. Okay, so a rocket, don't think we'll need the calculator for this one if it's just Newton's laws stuff. Explain, okay. These one might be the most difficult one to explain. A rocket mass of 10 newtons, including the fuel. Including the fuel, that's kind of important the way they said that. because the total mass is because it's the rocket mass and the fuel, is in deep space. So it's outside the effects of gravity, where the effects of gravity from any other object can be ignored. So we don't have to worry about weight force. When it starts to burn fuel, there is a constant thrust from its engines. Okay, so that means the applied force is constant. Explain how the burning of the fuel to make exhaust gas escape from the back of the jet cones can accelerate the jet forward. The rocket, I mean. So for the rocket, when it's blowing out the exhaust gases from the back, the exhaust gases are being pushed out this way, right? And so, according to Newton's third law, okay, whenever you can reference which law explains, you should say them. So in this situation, the gas getting pushed out this way by the rocket, therefore pushes back on the rocket that way. And so the rocket moves forward. Okay? So the gas gets pushed out, and the reaction force of the gas on the rocket pushes the rocket forward in that direction. Okay. And that's according to Newton's law. The gas pushes out with a force, and you're pushing something with a mass this way, that mass, this gas, is pushing that object the opposite direction. It's just like when we walk. We push on the ground with our feet, and the ground pushes on us. So the rocket pushes on the gas, and the gas pushes on the rocket. Okay? Gas out pushed by engine, reaction force from gas pushes rocket forward because the engine is connected to the rocket. Oops, forward. Okay. Okay. Explain what happens to the magnitude of the acceleration as the rocket is burning fuel. So there it is again. Going back to that, the mass of the rocket is 10 tons, including the fuel. Huh. Well, if we were looking at this and it's asking about us what is about acceleration and what is about the burning of the fuel. Well, the burning of the fuel accounts for the mass of the rocket, right? So we know that we know that acceleration is proportional to the inverse of the mass. And this is Newton's second law, where acceleration equals F net minus divided by mass, right? Now, remember it says the net force, the force is the thrust because there's no other friction or gravity opposing this is constant. So that net force doesn't change, okay? So if that is not creating more force or less force, that's constant. We don't even have to worry about force now. So really, the only thing changing acceleration is mass, any changes in mass. And then when you're burning fuel, and fuel is part of your mass, well, what happens to your total mass? Your mass goes down. And if the relationship between acceleration is inverse relationship, then your acceleration goes up. Okay? Because the amount of force from the engine doesn't change, but now it's pushing less mass. Okay, so according to Newton's second law, the acceleration is directly proportional to the inverse of the mass, so that as you burn fuel, the mass reduces, and therefore the acceleration increases. We good? Everybody still somewhat awake? Yeah, we'll just like maybe like another couple questions, you know, this one and one more, and then that'll be it for today. That's like almost 2 hours. Okay, so part C, the rocket burns 2 tons of fuel to accelerate to this velocity over a distance of this. So we got S. We got this. How much fuel will be needed to continue forward at a constant velocity of this for a distance of 2,000 meters? No calculation explained. Oh, wow. Okay. This is where people are going to get messed up. Why? Because you forgot Newton's laws of physics, and you forgot that you're in deep space where the effects of gravity from any other object can be ignored. There is no force except the engine. Okay? And according to Newton's second law, guys, right? It's the only net force. Okay, so the rocket burns 2 tons of fuel to accelerate to. There is your velocity now, whatever that is. It doesn't really matter that it took 100 kilometers to do it. It says how much fuel would be needed to continue forwards at a constant velocity, and the key word there is constant velocity. Constant velocity means F net equals 0. We don't need any more acceleration. Okay, so, and that is according to Newton's first law, that an object in motion will stay in motion. And that's what constant velocity means. It's already in motion and it will keep at that velocity. So no change in motion, in state of motion, really, state of motion, unless an unbalanced force, a net force, acts on it. So if we don't want the motion to change, we want this constant velocity, then we really don't want a net force. We don't want an unbalanced force to act on it. So how do we get no net force working on us? And the only force is the engine? We turn off the engine. You don't need any more to burn any more fuel because there is nothing slowing you down. There's no other forces. You're already moving at that 1,500 meters per second. You don't need to burn any more fuel because you're already at that velocity. You don't need to change it, and nothing is going to slow you down. Okay? A little bit tricky, but it's understanding those laws of physics, those 3 laws of Newton's laws of motion. Okay? Any questions about these 3 guys? Ooh, who's here now? Any questions? Hello, hello, bonjour. Oh, do we lose somebody? 1, 2, 3, 4, 5, and then me. Okay. Still same you guys? All right. No questions, huh? Okay, I'll try to find one more here. And then that's it. Maybe no more because my voice is getting. Oh yeah. Okay, why don't we do this one? Something like this. Okay, remember guys, you can always refer back to the video. I will put timestamps on the video so that you can go back and go directly to the questions you don't really understand that much and just review them again. Okay, so we have this brick. It's 3 kilograms. It's at rest at the moment, so that means F net equals 0 right now, okay? Which has a rough surface. The incline is 15 degrees to the horizontal. Identify the 3 forces acting on the brick by placing arrows on a free body diagram here, okay? Okay. Well, it's on Earth, so it's got gravity. It's got the weight force. You can write weight force if you wish. It has the touching the surface, which is perpendicular, so we have that. Normal force. You can write normal if you wish. And because it's at rest, okay, and this says it's a rough surface, so the only real force is the friction. The force of friction, or you can write friction. That's it. 1, 2, 3. These two always when there's a surface, and in this situation it has to be friction to keep it from rolling down, okay? Because these two right now, the weight force and the normal force are actually creating another net force down this way, okay? But the total net force is 0 because there is friction. And because it's at rest, that does not apply. There's none. It's 0 right now. Okay, that's one. Oh, that's A. Transfer the forces to the space on the right to construct a vector diagram to this situation. All right, yeah. Super easy. We just choose one. I always like to choose gravity first because it's always the same. It's always downwards. It's dependable. And then the normal force. Okay, it's the same. Goes that way. And then the friction force. Yeah, see? Just make a little path. We're adding them up. Net force is 0, so you started here, go all the way there, and you go back to there. That means 0. There's no change in the force. Okay, that's it. Friction. That's it. Calculate the force of friction acting on the brick in the equilibrium plane. Well, basically, this force here that was going to be because of those two is actually going to be, the net force is 0 because it's not moving, right? So this force equals that force. So really, if you want to calculate it, just find that, okay? And because this is right angle, again, you guys know how to, you should be able to go, okay, I know FG and I know the opposite, I need to find the opposite side, so it's going to be sine of that, but that opposite side is the friction, which is equal to these two's net force right here, okay? And then gravity is the hypotenuse. We identified this as the long side. There's the side opposite the angle. The angle always goes here opposite whatever is the net force, or in this situation is equal to the friction here, okay? Yeah, that's it. Let's find out what's the friction force. So FF equals this times that. So FG times sine of 15. Okay. Do we have mass or anything? Oh, we have 3 kilograms. That's it. So we need. So 3 kilograms times gravity sine 15. Okay. Whatever that is. 7.61. Okay, be careful how you write that. And 7 significant figures. Newtons. Up the hill. Okay, if there's a direction, it's along the slope. Along the slope. Sorry about my writing. That's it. Okay, I hope that's helped you today. We'll have another session on Thursday during the day. What do you guys prefer? Do you guys prefer the morning, like 9:30, or do you prefer the afternoon, like now? Okay, guys, that's it for the video too. Good luck. Okay, anyways, I stopped the video.